day 4 of our coding class. All right, so this is the coding session for the baseline machine learning model with linear regression and random forest. So this is the coding part of the lecture we had in day 4. All right, so for those of you in class, you're welcome, and for those watching this video on YouTube, you are also welcome. All right, so let's look at what we're going to be coding today. All right, so we're going to have a comprehensive line-by-line explanation of the baseline regression model pipeline using linear regression and random forest. So the first thing we need to do is to import libraries. All right, so we're going to import libraries. The first library we're going to import is the Pandas. So we're going to say import Pandas as PD. We're going to import NumPy as NP. We're going to import Matplotlib .pyplot as PLT. Also, we're going to import Seaborn. Okay. Seaborn has the SNS. All right, so importing important libraries, this is very important. And the next thing we need to do, also, we will need to split our data. We'll need to also use regression model as well. We'll also use random forest model, and we'll also perform evaluation metrics. So we need to also import some libraries that will enable us carry out all of these tasks. All right, so most of these libraries will be imported from Scikit-learn. So let's do that. So we're going to say from Scikit-learn dot. All right, so which libraries should we import first? Okay, we're going to load our data set, and then we're going to split our data set, meaning that we're going to partition our data set into training and test. So we're going to need a library to do that. All right, so that we can call a particular function called the train test split to perform that. So this is going to be from Scikit-learn dot model underscore selection import train underscore test underscore split. All right, so this is the method from Scikit-learn under the category model underscore selection that will help us do this. All right, so what next are we going to do? We're going to train a linear regression model. So we need a linear regression model. That means we need to import a linear regression model from Scikit-learn library under the category called linear model. So we're going to type the following code to say from Scikit-learn dot linear underscore model import linear regression. Okay, so once that is spelled well, I don't think we'll have any issue. Also, we're going to train another model which is a little bit powerful than the linear regression model, or which is a non-linear model. It's a random forest. So we're going to also say from Scikit-learn dot. Now, the random forest model is not a linear model. So therefore, it's not going to be imported from the linear underscore model. So rather, it's going to be, since it's an assemble model, it will be imported under the category assemble. There's going to be Scikit-learn dot assemble. Okay, assemble, that's spelled well, assemble. Import random forest. Okay, and since it's a regression model, we need to also mention that it's a regressor. Okay, so we say regressor. So the next thing we need to import is that we need to evaluate our regression model. Since this is a regression task, we'll focus on our loss functions, okay, the evaluation metrics. So we're going to also be importing this from Scikit-learn, but under the category called metrics. Okay, so Scikit-learn is a very large model. In fact, it's called the machine learning toolkit. All right, so we're going to say from sklearn dot metrics, because it's one of the matrices. We say metrics import mean underscore squared underscore error, comma, we have the mean underscore absolute underscore error. I think that's correct. And then we have the R square score underscore score. All right, so these are the three basic evaluation metrics that we will be needing in this practical class. All right, so the first one is the MSE. The second one we have is the MAE, which is known as the mean absolute error. And then we have, now let me quickly explain what mean square error does. The mean square error actually penalizes, it actually reduces the differences between the predicted and the actual. And then the root mean square error actually penalizes large error. And then the mean average the mean absolute error finds the difference between the predicted and the actual. And then you have the R square score, which explains the variance. Okay, it tells how the model deviates from the actual. All right, so let's see how this works. So the next part is loading of data. Now, in our previous class, we have been working with a specific data set, which is the featured engineered data set. The data set that we have cleaned, we have processed, and we have saved. We have engineered the data, we have saved it. So we're going to use the engineered data, the data that we have processed. So we're going to load the data, we're going to read the data using PD, which is pandas dot read underscore CSV, okay, into bracket. So we call this data feature dot CSV. Okay, so that will be in quotes. So we have to put this in. All right, so let's run the first cell to ensure we don't have any errors. In case we have any errors, we can quickly debug. All right, it says no module name Seaborn. All right, so that is not spelled correctly. We need SEA, and then let's run one more time. Okay, so that's run correctly. And then let's load the data set. It says no such file in this directory called this. Okay, so let's search where the file is. Where is the file? Okay, so this is the file. Let's copy the path to where we have the file. And then let's fix it. All right, so we have this. And then we fix and then we introduce the raw string. And then let's rerun this. So what we did is this. I copied the path where the data set is, and then I introduce it there. Remember, it has a backward slash. So because of the backward slash, I need to introduce the raw string, which is going to invert this backward slash into forward slash. All right, so once I run this code, it says no such file, this in this part, the CSV. Okay, so what do we have there? Let's see. Okay, it's called features. All right, so it's features. There is S. So let's run that. All right, so everything is perfect now. All right, so the next part we need to do, we need to determine the features for X and Y. So we need to prepare the data for X and Y. So we say X will be equal to df dot drop. So what this means is this: we're going to, from the data set, we need to drop the target label. The label we don't need to be part, that we don't want it to be part of the features that are not relevant, we need to drop. All right, so what are we going to drop? We need to drop the date time column, and we need to drop the, okay, let's see, let's know exactly what we need to drop. So let me say df dot columns. Yeah, this will tell us what exactly we need to drop. All right, so now we can tell the column names. We have date time, we need to drop this column. And then our focus, we want to predict the global active power, which means this is the actual power we consume in our house. So the household power consumption is the global active power. So that is exactly what we want to predict. So in that case, that is going to be our Y label. First, you need to determine what is your target. What is the target variable? What you want to predict? The outcome. So we have identified that this is the global active power because we want to predict how much power is consumed in a particular household. So therefore, that is going to be our label Y. So we're going to drop that in the future data. All right, so we're going to drop date time and the global active power so that it shouldn't be part of the features. So in that case, we're going to say let X, which is the training data, which are the features, the F dot drop. So that is the reason why we're dropping it. So we're going to drop the column. We're going to say columns. Okay, so which of the column? So we're going to indicate that is the data frame by using the square brackets and then the code. We're going to call it this name. So we're going to say the global active power. And then the next thing is we also want to drop the date time column. So that would be this. We need to drop this as well. All right, so once this is done, we introduce the closing parenthesis. So once we run this code, then this will automatically create for us, okay, it says drop unexpected argument. The column is not completely spelled, so it's supposed to be columns, meaning we need to have n is missing. All right, so the correct spelling is this, UMNS. So if we spell that correctly, that should run without any issue. Okay, and then once we view X, if we try to view X, say X dot column, what are we going to get? Now we're going to see that we have successfully dropped date, time, and global active power. So this is the features we want to train, all right, to make our prediction. So to predict the global active power. So in that case, what are we going to do next? We're going to assign Y, which is a target label. Okay, so Y becomes our target. So we're going to indicate that this is a data frame with a code. We're going to have this. All right, so now once we run this cell, automatically we have assigned this column to be the label as Y. So once you run the code, you're not supposed to have any error, but if you do, that's okay. So what could that be? It says error. Oh, we have while is supposed to be one label, not two. All right, so we're focusing on global active power. So let's run that. Yes, so we've gotten that correctly. All right, so the next thing we need to do, since we've been able to define the output target variable and also to define the input features, which is X, by dropping the target and the timestamp column. So the next thing we need to do is to split the data set based on the train test split method. So in this case, we're going to use the method that was imported from Scikit-learn, which is called the train test split. All right, so we're going to have it this way. So we're going to define X underscore train. So this is the training features, and then we have the X underscore test features, comma. Then we have the Y underscore train features, and then we have the Y underscore test features. So we're going to say these parameters, these variables equal to the method train test underscore split, okay, open and close brackets. So we need to supply some argument within this parenthesis, which we need to tell what is the features, what are the training features, and what is the target. So we've assigned capital letter X as a training feature. So that's going to be X, which is the data, the training data, comma Y, which is the target. And then we're going to specify the split ratio. So in this case, we're going to say test underscore size equal to 0.2. Now this means we set the test size to be 20%. Automatically, the remaining 80% is assigned to the training set. And because we want to prevent data leakage, like we said during the lecture class, we need to set shuffle equal to false, meaning that the data should not be shuffled, rather it should be split sequentially, meaning it should follow the time-based system in order to preserve temporal order, meaning that the older part of the data should be in the training split, while the test part of the data should contain the newer part of the data. In this case, we have prevented data leakage in order for it to predict the future usage of energy instead of predicting the past usage of energy. So what we're doing in a nutshell is to actually use historical data to make predictions for future demand of energy. So you need to ensure that you set shuffle to be false, else you're going to have data leakage. All right, so you're going to have a wrong data split that will affect the performance of your model or affect the integrity of your model. Very important. We're looking at the integrity so that you can maintain ethical standard and ensure that your model follows all standards. All right, so the next thing we need to do, we need to load each of these models. So let's load the regression model. All right, so we say OLS equals to the linear regression. So what we have done, we have loaded this model into the variable called OLS, and the next thing we want to do, we want to train the model. So we say OLS dot fit. So once we say dot fit, it means we need to train the model by fitting this model into the data. All right, so what data we have? The X underscore train, and then we need to supply the label, the target for the train, because this is a supervised task. So we need to introduce the data and its label. So we have y underscore train. All right, so we have both the data, which contain the features, and also the target, which is the label. All right, so once we do this, and then we run, right, it says x underscore train is not defined. So we have x underscore train is not defined. All right, so we have that to be x train. Okay, we have y train from this part. All right, so I see we did not run the cell above. So in this case, we're going to have errors. So let's run this cell. When we carried out the split, train test split ratio, we didn't run the cell. So let's run the cell and we're not going to have any issue. All right, so successfully we have trained the linear regression model. So the next thing we need to do, let's predict this model. So we say y underscore predict, PRD underscore OLS equal to, we say OLS, which is the model that has been trained, dot predict, which is the method to predict. All right, so we're going to be predicting based on the test set, which is x underscore test. All right, so once we do that, run, and then the result, the prediction has been saved in this variable, which is the predict. And later on, we're going to compare, see the differences between the predict and the actual label. So in that case, we're now going to be using the label of the test set, which is going to be the y test. All right, so now we're going to also train for random forest. So for we to train for random forest, all we need to do is to load the model. We call the random forest equal to, so we say random forest regressor. Okay, so since this is the model, we have some parameters we need to set. So we say n is the number of tree, which is the n underscore estimator, which is the numbers of trees we want. So let's, for quick competition, so let's say 5. Okay, numbers of tree, let's say 5. Now take note, Now, the lesser the numbers of your estimator, also it affects the performance. It can result to a lower performance and also can also lead to risk of underfitting. While if you increase the value too much, it might increasing the value increases the performance as well, but there is a risk of overfitting. All right, so you just need to get the right number, the right value. All right, so this usually requires you to carry out optimization, hyperparameter optimization, where you have to check and try different values. All right, so you can use an automatic system which is called the grid search for such kind of ablation study so that it's done automatically without you having to change the value manually. So you can create a range of value to undo that. So the next parameter we need to set is the random state, which is equals to 42. Now this allows for reproducibility, meaning that each time you run this model, the same result is going to be what you get, right? So the result will keep changing. Right, so this is the reason why we set a random state. So the constant that is usually used universally is 42, but then you can supply any constant value, it will still work. All right, so the next thing we need to do, let's run this cell. All right, so that once we have an error, so we can tell what's going on. All right, so once we do that, I think we have an error. So the error is saying that you got an expected argument estimator. All right, so that is supposed to be estimators. Okay, so oversight. All right, so we have loaded that into the variable. So the next thing we need to do is to train. So for we to train just the way we train linear regression, rf.fit into bracket, we need to fit it to the data. So just exactly what we have done. All right, so we're going to compare these two results to see which one is better. So we're going to do the same. We're going to run this to train. And then let's see how long it's going to train. Then we also need to predict as well. Okay. And then save the result of the prediction so that we can use it to determine the loss value. All right, so we have that as y predict underscore rf equals to rf dot predict, or predicting based on the test value, the test set. So the next thing we need to do is to evaluate the model. Let's see how the model performs. Let's see the loss value. Okay. Now the next thing we need to do is to define the function, the evaluation function. So we're going to say df, which is to define the function. We're going to say df metrics. So let's call this metrics. Okay. Right. So it's done training, and then we predict, and then we say metrics. We pass in some parameters. We say y underscore train, comma, no, we say y true rather, which is the actual target, y true underscore, we say y underscore predict. All right, so this is the predicted result. And then we could provide the model name just to differentiate between the two models. Okay, model name. All right, so we have this. And then in this case, we have defined a function. So the function called matrices. All right, so what do we want to show? All right, so the first thing we would like to print, model name. Okay, the next thing we would like to print each of these losses. All right, so we're going to have mean square error. So these are the losses that was imported. Okay, so we have them. You can just simply copy them. Okay, put this in quote. We have this in quote, and then we have this. Okay, we have print in quote. Then we have this close the bracket, and then we have print in quote. All right, so since these are methods, so all we need to do is to ensure that we pass the right argument within the method. So we wouldn't be needing this code. Okay, since the model name has been defined. The model name has been defined, so we won't be needing this code. This is a method directly from Scikit-learn. So we'll be needing the code. So all we need to do is to pass the right argument within this method. All right, so for the mean square error, all we need is we need the true value and the predicted value. Okay, we need the y true and the predicted. So also we need the true value, which is the actual, and the predicted, which is the y predict. All right, so those are the parameters, the arguments we need to supply, or probably the parameters we need to supply within the parentheses of the method. And then, now if you notice, we have a mean square error, we have mean absolute error. Okay, now let me repeat this. Because we need the root mean square error. So that means we need to do something. We need to say np dot square root sqrt. So this will take the square root of the mean square error. Okay. So in this case, yes. So we're going to see. So now let's see what the result will look like. So let's run the cell if everything is okay. All right, so since we have been able to define the metrics function, the next thing we need to do is to print metrics. Okay, so we have the metrics, which is this. We have the define. Okay, we put that into parentheses and then we supply the information. So this is y test is the actual label of the test set, comma. Now we have predicted this model. We have trained this model, and this is our prediction. Now let's see the differences between these two. All right. Let's see the differences between these two. And then we have in code OLS. So this will tell us this model. And then also we're going to do the same for the random forest model. So this is going to be a random forest model. This is going to be random forest model. Okay, so let's run this. If there's any error, we're going to fix it. All right, so we can see the result for both model. We can compare. We could see the result for the mean square error, which is very large. We could see for the square means, for the square mean square error, root mean square error rather, and then for the mean absolute error, and then for the R square score. All right, so the interpretation of this model is this. For the mean square error, the unit is quite different from the unit of the target variable. So that is hard to interpret. Interpretability is a little bit hard. So the right metrics will be the root mean square error, which return the unit which is the same as that of the target value. So that helps us to penalize large errors. So in that case, it makes it very easy. So we could see that the error is quite low. And also for the mean absolute error, we could see that the error is also very low. And then for the R square, which explains the variance, we got 0.999. So which is multiplied by 100, that will give us 99.9%, meaning that we have just 0.1% variance, meaning that the prediction of the model is near perfection, near 100 percentage. All right, so now we need to make this result a little bit fancy. Fancy meaning that we should be able to introduce some kind of custom display. All right, so in this case, let's see how to introduce some custom display so that we can have the result well presented. So we're going to use the F string. So the F string in Python allows us to display our result in a way that looks appealing. All right, so we're going to say F code. Then we're going to introduce the curly brackets around the main argument. Right, so we're going to introduce this around the main argument, and then we're going to introduce another dash, and then you put the code. So if you do this, it's going to give some nice display. And then for the second one, F code, and then we call this MSE colon, and then we place the main argument in curly bracket. All right, and then we also place this in curly bracket. All right, so that's looking very nice, and then we'll put the code. All right, so the same thing we're going to do for this F code. This is arrow MSE code. We'll put that in curly bracket. You also put this in curly bracket. Then we introduce the code. So we have for this as well, code. This is MAE, and then we put the colon, and then we introduce the main argument, the main parameter, that's the main argument in the curly bracket. And then we introduce the code. All right, so in this way, okay, so let me see. Finally, we have the arrow square, or we say the arrow score. Introduce the curly bracket, introduce the curly bracket, and introduce the code. So you have to run this all over, and then run this all over, and then run this all over. So in this case, the result is properly presented. We could see the name of the metrics and also the result in front. But then we need to reduce this to 3 decimal places. So all we need to do is to go into the curly bracket and then introduce the colon and the full stop and say 3F, okay? And then do the same for the rest. And then this is going to limit it to 3 decimal places. Now, don't forget you have to do this within the curly bracket. Then if we run, we're going to get 3 decimal places. All right, so this is awesome. So the next thing we need to do is to visualize our plot using the scatter plot to see the nature of our graph, to see the actual and the predicted. So let's see the margin. Let's see how well the model is predicting. So let's see how close the prediction is to the actual. So the next thing we need to do is to say plt dot figure. All right, so this is a matplot function. All right, so it's a method. So plt dot figure. Now we need to specify the figure size. So we say fig size equal to, into parentheses, we can say 6, 6, and then we introduce another closing parenthesis. All right, so we introduce scatter plot. So we're going to say plt dot scatter into bracket. So we need to remember we're dealing with the label. All right, so we're going to take the label, which is the y test, and then we need to also introduce the predictive result, which is the prediction, and then we say plt dot plot. All right, so we're going to plot the y test. So we're going to say dot minimum, and then comma. We're going to have the y test dot maximum. So we're going to introduce the square brackets, and then we need to also do the same for the y test and the y test as well, for both y test minimum, maximum, y test minimum, maximum, and then we introduce the line of best fit to show. So we have code arrow dash dash. All right, so it's going to be a red line, a red dash line. All right, so once we run this, it's going to produce for us the graph. All right, so this is how the graph looks. So we can see that the prediction, so we can see that the line falls within the point, the data point, for both the predicted and the actual. So what the model is predicting is exactly the same as the actual label. So let's make this look a little bit nice. So we need to introduce some description. So say plt dot title. Okay, we say title. So what title do we want to provide? So put that in quote because it's this string. So we're going to say random forest, okay, which is actual versus predicted. All right, so we also need to introduce the label for each axis. Dot, we say x label. What is going to be the x label? The x label will always be the actual. We're going to say actual, and then the y label will be plt dot y label. This will be the predicted. All right, so the next thing we need to do, if you run this, oh, it says we have an error. What's the error? Error. It says, okay, this is y label pl dot y. Okay, and then the label, we have a name L. Okay, right, so we can see the name, the label has been introduced. Now let's show the plot so that we can get rid of those unnecessary information. So we say plt dot show. So this is going to display the plot without any other irrelevant information. So all right, so we need to also, this is for the random forest. So what about the linear regression model? So all we need to do is to change this to OLS, which is the linear regression model. And if you run, it says, so we need to change this to linear regression as well. So say linear regression, right? So when you run this, you're going to get these two results. So it shows that the model is performing very well. Both models are doing very well. Okay, so we need to also show the residual plot. So all we need to do is to say residual. So let's use residuals equal to, we have the y underscore test minus, okay, y predate. So we have y underscore predate underscore OLS. Right, so once we have this, we can run our cell. So once we run the cell, it stores the differences between the predicted and the actual. All right, so let's calculate the residual, the prediction error, which is the residual. So the residual is nothing but the prediction error, okay, for the test set. So we're going to introduce the same kind of graph, okay, it's the same function. We're going to introduce the same method, rather. So we say plt.figure, and then let's set this to probably 10 by 4. Let's change the value. And then we'll have the plot residual. So we say plt.plot. Okay, so we're plotting residuals. So we have the residuals dot values, right? Right, so the next thing we're going to do is to set the axis line. Okay, so we're going to set that to say plt dot axis h line y equals to 0, and then we're also going to set the color and the line style. All right, so beginning from y is equals to 0, so we're going to set two other parameters, color equal to, we're going to use red code. So R stands for red, and then we're going to say the line style is equal to, so we're going to use dash dash dash, which we put in quote, dash dash in quote, then close the bracket. So the next thing we need to do is to give the title X label, Y label, and show the plot. All right, so this is similar to what we've done previously. All right, so let's see what happens. So let's call this residual plot. So we have time against residual. So the X is going to be time in this case. and then the y is going to be the residual. Don't forget, it's over time. So therefore, we want to see the difference. It means the prediction error on the test set over time. So if you run this, we shouldn't have any error. But let's see what happens. Okay, we have supposed to introduce dots at this point so that we can have the line. Okay, so I'm not saying the line. Okay, so we introduce dot. All right, so we could see the line of the plot for the residual. Okay, based on the RF, the OLS model. So we're going to check for the RF model. I could see that the result is not the same. Now, this goes to tell us that the residual over time is visualized to check for biases and variability. Now, both graphs we could see that the OLS show a lot of variability over time, and then for the random forest model, we could see that the variability over time is not as much as the OLS model, meaning that the random forest model is more powerful than the OLS model. Okay, so we could see the different residual plot telling us that the prediction error for the random forest is quite lower compared to that of the regression model. So this is how you can tell and compare your results. All right, so finally, we're going to check the feature importance plot, which can only be used on the random forest model. It's not possible for we to check the feature importance for linear regression. Or it can only be used, in this case, it will be used for the random forest. So this is why we move from a very simple model to a more or moderately advanced model where it allows us to check for more features that helps us understand the predictive process of the model. All right, so now we can go one step further to see what we can visualize. What can we see? So that what can we tell about the model? What can we tell about the features? All right, so we're going to introduce the feature plot, which is the feature importance plot. So we're going to say importance should be equal to the inbuilt function that we have. So we'll say rf dot feature underscore importance. Okay, in that case, underscore. So if you run this cell, we shouldn't have any error. All right, so the next thing we need to do is to introduce the plot. So for this is a straightforward plot. All we need to say is the features. So we say, let's call this variable feature underscore df will be equal to, we say pd dot data frame, okay, into brackets. So we look at the features, which is in code to say feature column, we'll say x dot, okay, coming from the features that we have defined, okay, columns, comma, we're going to say importance. Quote, column, then we say importance. The next thing we need to sort So we say feature underscore df dot sort underscore values. So we're going to be sorting by importance equals to importance. And then this should be a quote. And then most importantly, we need to also set, is it ascending? No, we're going to set that to false. So rather, it will be descending from the top to the least. That's what it means. So the next thing we need to set is we need to say in place true. We'll close the bracket. And then we need to say plt dot figure into bracket peak size equal to. So let's set the size to 10,5. Let's close the bracket. And then we say SNS, which is a Seaborn plot, which is built on Matplotlib. It's a very powerful and high-level visualization tool that allows us to plot appealing graphs for excellent visualization. So we say we're going to be using a bar plot, right? So we have the bar plot, we have the variable x equals to important, comma y equals to features. So actually the next parameter is going to be the data, which is nothing but the fit underscore df. And so call it fit underscore df. We're going to give this a title. We're going to say plt dot title. What title are we going to give it? Feature importance. I think that's straightforward. Close the bracket. So once we do this, the next thing we need to do is to say plt dot show. Okay. So once we run this code, if we have any error, we're going to debug it. It's okay. All right. It says, where do we have an error? It says the fit underscore df is equal to data frame feature. Okay. Colon. It says we have an error at that point. Okay. So let's address this quickly. So what is the feature? It says the column. Okay, so let's see. It says we have an invalid syntax. We have columns. Okay. And then we have importance. So something is wrong. Okay, I think we have importance. The name here is S. We have the importance, which is S, and then we have a double quote, which is supposed to be a single quote. All right, so that is solved in the first part. Then it says we still have one more feature that sort values, okay, by equals to importance, ascending, and true. So it says invalid syntax. All right, so let's address this quickly. So pd.dataframe feature. All right, so the issue we have is that it should be placed. So this is the argument. So I think the bracket is missing. Yeah, what if we introduce a curly bracket? That is exactly what is missing in this part. So we have a curly bracket. Okay. And then we have the features. The curly bracket is introduced wrongly. Okay, yeah. Okay, I think there was a wrong introduction of the curly bracket. Okay, so that works well. Right, so in this case, we can see that the most important feature is the apparent power. Okay, it means the apparent power contributes significantly to the decision making of the model. So this tells that this is a very important feature when predicting power demand, future power demand of a household. So this is very important. So this plays a crucial role. So this has helped us to visualize the importance of each feature using the horizontal bar plot. So this gives an horizontal bar plot just like we have seen, and then we can appreciate the most influencing or influential features. So if you've gotten to this part, it means you have learned something significant today. All right, then, we're going to say goodbye and watch my next video on the week lecture 5. So stay tuned as I see you next time. Goodbye.